This is very easy to deal with. This is a good rule of thumb from my personal experience. There are several geometric shapes and structures that need to be understood with organic chemistry. Understanding the prior concept of general chemistry is essential, however, to really understand what's going on with organic chemistry. Organic chemistry is the chemistry of carbon, C, oxygen, O, hydrogen, nitrogen, phosphorus, P, sodium, Na, chloride, Cl, and some metals thrown in for seasoning in good measure. We'll be dealing primarily with covalent bonds in the organic chemistry. From the valences and groups of the periodic table, recall that carbon has 4 available binding sites. Nitrogen, boron, and phosphorus generally have 3. Oxygen has 2 bonding sites for covalent bonds and also 2 pair of electrons that are out there that will attract hydrogen bonds and allow for hydrogen bond formation. Group 1 includes the hydrogen, sodium, and potassium. Each of these have 1 available bond. They're also the most likely to have the ionic bonding. As alkaline metals, they accept protons well, better than group 2, such as calcium and magnesium. Group 2 are known as the rare earth metals. Magnesium and calcium each have 2 available bonds, and they can also ionize and go to the Mg++ or the Ca++ form for their ionic bonding. Beryllium really does not participate very much in biology, so we're not going to worry about that. Metals also bind into these organic chains. Metals are often catalysts for our enzyme systems. They're frequently involved in electron transport redox type reactions for energy transfer. Metallic compounds also often oxidize, losing or gaining an electron or 2 or 3 as part of their function and their role in these compounds. Metals are generally chelated. Chelated means essentially that they're wrapped in a hydrocarbon chain, which enables their biologic function, activity, and interface. Organic chemistry nomenclature. The most basic structures in organic chemistry are carbon chains, typically with hydrogen, together known as hydrocarbons. The basic naming is done by the number of carbons in the chain. 3 carbons would be propane, with the last 3 letters designating the carbons as being joined by single bonds. The top drawing shows the hydrogens. The bottom drawing shows the bare carbon chain. Both types of structure are commonly used. Again, each carbon has about a 120-degree angle between the bonds, and if you look at this compound below, R is anything. It could be another hydrocarbon chain, it could be an element, it could be anything at all, but the important concept is to look at that central carbon, and you see there's essentially a straight line to the left for the R, there's a straight line going straight up for the H, but one H has got that dashed line reflecting that it's behind the carbon to some degree, and the other one has the triangular bond indicating that the hydrogen is actually sticking out of the screen towards us. So carbon chain types, if it's all single bonds, the compound will end with the letters ANE. If they have double bonds, it will end in ENE, and triple bonded carbons will be YNE. 2 carbons would be prefaced with an ETH, 3 with a PROP, 4 with a BUT, 5 PNT, 6 HEX, and so on. So a 3-carbon chain with just hydrocarbon with hydrogens around it and no double bonds would be propane. If there was one double bond in the middle of that, that would be propene, and if it was a triple bond, it would be propyne. Double bonds do not allow carbon rotation as a single bond. Well, the single bonded carbons can just rotate around in a 180-degree to 360-degree spin. But when there's a double bond, that spin is not possible. Also note, with a double bond, the hydrogens are missing, thus this carbon chain would be called unsaturated. Double bonds are denoted either as cis or trans. In cis, you'll see that the CH3 groups are both on the same side of the double bonded carbons, and the hydrogens are on the same side below. But in the trans configuration, one of the CH3s is on the top and the other one is on the bottom. This is essentially an asymmetric bond molecule and can form what we call an isomer. Trans fats are the bad fats. Our enzymes don't degrade them well. A chiral molecule has an asymmetric carbon atom with a non-superimposable mirror image. Carbohydrate sugars are D designated, amino acids are L designated. And what this means is that polarized light passing through a pure compound will be rotated a little bit to the right if it's a D or to the left if it's an L. And if you look at the diagram below, you'll get a better handle on exactly what that means. You'll notice that the R is toward the middle on both of them, the right hand and the left hand. There's a COOH on the top. There is a NH2 on the bottom, and hydrogen's off to where the thumbs are located. So one of these compounds would rotate polarized light to the left, the other one would rotate it to the right. Functional groups. Alcohols have an OH group and they end in OL. Alkyl halides have a carbon bonded to a halide group, members such as chlorine or fluorine. Ketones have a carbon with a double bond to an oxygen. They end in ONE, such as acetone. Aldehydes have a carbon with a double bond to oxygen and a single bond to hydrogen, ending in AL as a term. Carboxylic acids have a carbon with a double bond to oxygen and an OH bond, which can donate a proton. They will be termed as an oic acid. Ethers are carbons with a central oxygen. Esters are sweet-smelling. They're similar to ethers, but there's a double bond on that oxygen, and they end with the letters OATE. Amines have an NH2 group bound to the carbon with a prefix of amino. Amides, on the other hand, have a carbon with a double bond to oxygen and then a single bond to the amine group, and the term that ends with the suffix amide, amide. Polar characteristics of organic chemistry are important. This is not polar as in the North Pole and get your parka. This is polar as in dipoles like a magnet and where the electrons tend to be concentrated. Hydrocarbon chains are what we call hydrophobic or water-hating. Oil does not mix well with water. Oil is a hydrocarbon chain. Ionic compounds, such as alcohols, carboxylic acids, charged groups with sulfates, phosphates, have an electric charge at one end of a carbon chain and a long hydrocarbon chain behind them. They can act as detergents. One end of that molecule will mix well with water, the end that has the polar charge to it. The other end of the hydrocarbon would not mix well with water. So in the diagram below, R could be a 30 carbon chain or whatever you want it to do. And in this case, it would react very poorly with water. But then when you put a phosphate group, now all of a sudden, look at all those oxygens you have at that end. Those oxygens are going to kind of suck the electron cloud of the molecule down to their end of the chain and put some charge there, which means it will react well with water, and it will be the hydrophilic or water-loving end of the carbon chain. And then the other end of that carbon chain, where there is no polar effect of excess electrons, would be known as the hydrophobic end, or the fatty end that does not want water. Try to visualize the electron cloud of this larger molecule. Okay, it would likely be composed of carbon, oxygen, phosphorus, hydrogen, and again, the oxygen, the phosphorus, sulfur, whatever else is there are going to be kind of sucking the electron cloud a little bit closer down to their end of the chain, leaving the other end of the chain a little bit deficient in electron cloud. The electron density will interact well with water in a water-loving manner. The hydrocarbon chain will not want to interact with water, but would rather react with other hydrocarbon chains. This interaction in an aqueous water-based environment, the phosphate groups will face outward, and the hydrocarbons will form their own layer. We're going to get into more of that in the cell biology section, which will come after the chemistry section. Hydrophobic, anybody who's tried to separate a thin plastic baggie on a cold day will know that plastic wants to bind to itself. Even though there's no glue, the plastic carbons like to stick together, and that's part of the hydrophobic aspect. It doesn't like water, but it does like to stick to itself or others like it. This happens every day in our body. These long chains of atoms are made of, again, of carbon, nitrogen, oxygen, phosphorus, hydrogen, sulfur, and other elements. As these long molecules are formed, they assume specific configurations. Amino acids and peptides and proteins are what we'll talk about next. This is the basic chemical structure of these guys. And you'll see at the one end, there's an amino group with an NH2. At the other end, there's a carboxylic acid group with a C double bond O and an OH. Now, if it's all by itself and not bound into a long repeating chain called a polymer, that amine group with the nitrogen, where there are some other paired electrons, will also have a bit of a participation in hydrogen bonding and ionic separation. So it will tend to like water and bond well with water. The same thing will happen at the C double bond OH end, but what will happen ultimately is these two guys can get together, linking end to end, and we'll go into that in a little bit. But amino acids are basically pretty simple compounds when you get to the basis of them, and you'll see there's a red R below that. There are 23 main amino acids, and the R is different in each one of them, but the basic two-carbon chain up there will be the same in all of them. There are the building blocks for peptides. Peptides are basically short chains of amino acids. They link the carboxylic acid group to the amino group of the next amino acid, producing the dipeptide plus a water molecule. So you can see in this diagram how the water was formed when these two guys got together. The primary structure of a peptide describes the constituents in a linear sequence as it's formed. A peptide is a term to describe a short chain of amino acids. A protein would be a much longer chain. Carbohydrates, such as glycogen, are repeating sequences of sugar molecules. There are a variety of different sugars that exist. They're all described based on their arrangement of atoms into groups around the carbon chain in an isomer fashion. Again, isomer, think of the diagram earlier that had the two hands, and that gives you an idea of what those molecules will be like. Aminoglycans are peptides or protein amino acid chains with attached side chains of carbohydrates. They work well to absorb water and they lubricate surfaces. They're present in our joints, for instance. The secondary structure of these peptides and other molecules refers to the highly regular repetition of local substructures. These are defined by hydrogen bonds and ionic attractions. These bonds cause the folding of the chain that undergoes as it's being formed. The angles of the elements joining together also cause the chain of smaller units to fold on itself in a specific format. Silk is a sequence of beta-pleated sheets of a monomer or repeating unit that forms a polymer or a series of repeating units. Polyester is a repeating sequence of ester chains as described below, or as visualized below. The tertiary structure refers to the three-dimensional structure of a single, double, or triple bonded protein molecule. Alpha helixes and beta-pleated sheets can fold into a compact globular structure. This folding is typically driven by non-specific hydrophobic interactions. It's not so much something that water gets into, it's more the carbons and hydrogens pulling things together. This structure is stable only when parts of a protein domain are locked into space by specific tertiary interactions, such as salt bridges, hydrogen bonds, and disulfide bonds. As far as a salt bridge, remember what I said earlier, that a carboxylic acid will tend to lose that protein and gain a negative charge. The amine group at physiologic pH will tend to gain a proton and have a slight positive charge. The salt bridge refers to the fact that there's a positively charged and a negatively charged. They're not covalently bonded, but they do kind of tend to attract each other. Sulfur will do the same thing to another sulfur, and of course hydrogen bonds we've already reviewed. And this is an example of what these things would look like. Quaternary structure. This is a three-dimensional structure of a multi-subunit proton and how the subunits fit together. It's stabilized by non-covalent interactions, and typically disulfide bonds is a tertiary structure. Hemoglobin, for instance, has an alpha and beta chain that each contain iron in either the ferrous F2 normal state or occasionally the ferric F3 plus abnormal state known as methemoglobin. This is a state that cannot transfer oxygen. It's oxidized and needs to be reduced from ferric to ferrous in order to function. You can just barely make out the 4 iron atoms with the 2 green alpha chains and the 2 yellow beta chains. We'll review carbohydrates now. Carbohydrates are basically common biological sugars that generally have 5 or 6 carbon atoms and are more properly called sugar alcohols due to the R-OH of repeating structures. They can be straight chains or ring-shaped, and in the natural physiologic state, they can very easily and quickly change from these two shapes. Glucose would be an example. Here you have a cyclic glucose, a circle of glucose, and it can also convert into a straight chain. For the sake of ease of drawing, straight chains are usually a little bit easier to visualize, but if you pay attention, you can look carefully at the cyclic form and have an understanding of how that works too. Looking at the straight chain, you'll see that there are hydroxys on the right, then the left, then 2 on the right. To change from glucose to a different molecule, a different sugar, you'd just simply take the OH, the hydroxy group, and move one of them onto the other side where the H is. And these are asymmetric carbons because of the C double bond O and just the overall format of them. And the C double bond O up there, one side leads off to an H, the other side leads to the long complex hydrocarbon chain that for shorthand will be described with the letter R. Hexoses are 6 carbon sugars, and you can see that between glucose and mannose, there's just some differences on where the OH is. And you have the linear form above and the cyclic form below. Pentose is a family of 5 carbon sugars that can also be in straight or ring form. Remember that all sugar carbohydrates are D isomers that rotate polarized light to the right. The L isomer sugars are not biologically active. With amino acids come in the L form, and any D form amino acids, again, would not be biologically active. Ribose is a typical pentose, or 5 carbon sugar. It's used as part of the nucleic acid base structures of our DNA, and this is what it would look like. Glycogen is a branched chain storage form of glucose that is primarily found in liver and muscles. It can be burned to produce energy without oxygen, but this process is quite inefficient. And this is what glycogen would look like, and you can see there's a couple of branches. There's, let's see, 1, 2, 3 branches available on this particular diagram. Sterols will be the next area that we're going to review. Sterol is the term for a basic structure. This is what it looks like in shorthand. And you can see that basically there are three 6-carbon rings and 1 5-carbon ring. And these are basically fats. This class would include cholesterol. And despite all the bad press, cholesterol is very important. It's got a bad rap. You can see the basic 4-ring structure, and then on the upper right-hand corner there's a hydrocarbon chain, in the lower left-hand corner there's a hydroxy chain sticking out. And this basically is the big difference between a sterol and cholesterol. Cholesterol forms the basis for sex hormone formation. DHEA, dihydroepiandrosterone, is the parent compound for the sex steroids, and this is what it looks like. And you can see it's got pretty much a typical sterol structure. In the upper right-hand corner, there's a double bond to oxygen that comes off the pentamer carbon. Testosterone is a little bit different. Instead of a double bond to oxygen, there's an OH there. And in the lower left-hand corner, where there was an OH, there's now a double bond to oxygen. Estrogen is a little bit different. It's got the OH in the bottom and it's got the double bond O back at the top, similar to DHEA. So you could really almost say that it's just a couple of hydrogens, and where they're placed, there's a difference between men and women. Vive la différence, eh? And then progesterone is another sex steroid. And on the top of the 5-carbon chain, there's another carbon chain there with 2 carbons added to it. And in the lower left-hand corner, you see that there's the double O like there is with testosterone. So that's the basis of the sex hormones and what makes us men and women. Fatty acids are another set of building blocks for structural fats. And as we discussed earlier, if there's a double bond, and if you look at the bottom diagram, the 3rd and 4th carbon from the right, there's a double bond there. Where that double bond is, there could be room for 2 additional hydrogens, but they are not there. So this is an unsaturated or a monounsaturated structure that happens to be in the cis format. You can see the 2 hydrogens are both sticking up in the same direction. On the other hand, up at top, the hydrocarbon chain it's fully saturated. There is no room for any more hydrogens there. Fatty acids will have a phosphate group added at one end. So phosphatidylcholine is an essential component of a biological membrane. And this is what these look like. You can see the phosphate group and this one in the middle. It's a sphingomyelin, okay? And if you look below, you can see another compound where they've just sort of folded it over. It would have been a very long compound. It wouldn't have fit all in one piece of paper. So they just kind of folded it over in the middle where the action is. And you can see there's a phosphate group attached in there with an amine. Triglycerides consist of glycerol with attached fatty acids. So this is what glycerol looks like. It's basically a 3-carbon chain with 3 hydroxy groups on it. That's the OH group. And then in triglyceride, you've got long chain fatty acids that tack into that OH group. And now you've got an unsaturated triglyceride. And it's unsaturated because you can see where there's some double bonds drawn in there. If it was a saturated triglyceride, there would be no double bonds. It would all be filled with hydrogens. There are some basic rules for structural components. A polymer is composed of repeating identical monomers, such as repeating glucose molecules, that can form starch if it's unbranched, or if it's branched, it will form glycogen. When monomers gather and link up to produce a polymer, generally water is produced. Conversely, a polymer can react with an acid, alkaline, or enzymatic reaction to break into its constituent monomers. Basic rules: continued long complex molecules of different compounds can also form so that amino acids form peptides and proteins, or glucosamines, in which amino acids join up to carbohydrate and then peptide chains. Again, a peptide is a short protein or chain of amino acids. Peptides can also link up with fats. Sugars, carbohydrates can link up with fats or peptides. All combinations are used and they all work well together. So again, a peptide can join to other peptides, lipids, which is a fat, sugars, carbohydrates, or a carbohydrate can join to carbohydrates, lipids, or peptides. Lipids can join to lipid, carbohydrate, or peptide. And also other moieties can link in, including metals, phosphate groups, etc. I hope you've found this beneficial, this review of general and organic chemistry. We're going to take these concepts next and relate to molecular biology and how our basic cells function. And from there, we'll move further through the vitamins, minerals, supplements, and everything else to better understand how they work in our bodies. Thank you for paying attention. What are cells and what do they do? My name is Rusty Owenbrink. I'm a board-certified osteopathic family physician with over a decade's experience as an integrative physician. And we're going to talk about basic biology in this review, starting with what our cells are and what it is that they do and how they do it. Basic cell biology. There are some basic concepts such as cell theory. In 1838, Schleiden and Schwann proposed that the cell is the smallest form of life. if we consider viruses, prions, etc. as cells. Cells arise from pre-existing cells. All forms of life are made of cells or collections of cells. Since then, we've learned that certain cells are differentiated for different functions. Some cells secrete chemicals outside of themselves to control their immediate environment or perform specific tasks. Fibroblasts, for instance, make collagen fibers which strengthen tissues. White blood cells secrete cytokines which influence other nearby cells, recruiting more white blood cells to the site of the infection, etc. Cells are classified as fundamental units of structure and by how they obtain their energy. Prokaryotes are the typical bacterial cells. They have no nucleus and contain a cell wall. Eukaryotes, that's us,